So slope can be like a cut by super engineering or construction activities, or it could be a lateral slope. So on the slide here, I give you some picture on some failure, what may goes wrong. So I for this couple like a picture here, I don't have the site name. I just Google that really quick, but like want to give you an idea like what kind of scale of the mass failure here. So it could be a small scale slope problems. It could be happen at your backyard, or at a slope that like on a small road that like end up like countryside of of uh, area of a road that like got be malfunctions, no casualty or no loss of properties like when this happens. But you could be like when slope fell, you could be in another level. If you have massive like a slide that come down, you can lock down the whole highway, and then you can like jeopardize like the whole city, or like paradise like the whole city engines or highway for a period of time. So it could be quite dangerous. And now we're talking about the loss of human life, and also top loss of important like structural properties right there. And there's another well, like this is also like a huge concern in the mining industry, because in the mining site we push the limit. We want to have a cut that as deep as possible, to maximize the profit. And oftentimes, like mining sites is very risky, because we're pushing the limit. We want to like go as deep as go as far as we want, and as a result, we got a very steep slope, and the steep slope will end up with to be failure. So I put on a case history for some of you if you want to read about it. On campus, I upload like 2 papers regarding in United States, like case history, a relatively recent like case history. So 2014 happened at Washington. So also, that was the time that I'm doing my PhD at Texas, and that time there was a time that everyone talk about this case history and this happens, and also a time that I have a lot of time to dedicate myself to understand what's going on. So also Washington is like 2014, there was a landslide, and massive enough that like the Americans or the West Coast, like people feel pain about it. So if you want to learn more about this case history, I upload like 2 very well documented papers on campus. So feel free to read about it. So now the question is, why this happened? What is the cause of slope failure? So why this happen? So any guess? Why does a slope fail? What would be the potential cause? So anyone? Any guess? Just because old enough and they fell? Why would a slope fail? Anyone? More drying force and resistant force. Very good, David. So where does the drying force come from? And where does the resisting force come from? Anyone? Maybe start from the drying force thing. Yeah, very good. So the drying force could be earthquake. Yeah, and the resistant force could be loss of strength. Okay, very good. So an earthquake can happen, and then that would be provide you like a lateral loading force to trigger the landslide to happen. And loss of strength. So why loss of strength happens? The ground is the ground. Why the strong the somehow there will be like a loss of strength? Anyone? So the case history of the Washington also is after the heavy rainfall. Slope stability may not, like the rainfall induced like a landslide may not be a much concern in Southern California, but like it will be a concern in the northern part of the West Coast where you have more rains, and also in some tropical area, the tropical area in the country near the tropicals like areas, they have a lot of winds like during the summer times, that could be the concern. Yes, underground water table, very good. So when you have a lot of winds happening, so the groundwater tables, well, this is the slope. Let's draw a slope. So if the groundwater tables goes up because of the rain seasons, so the effective stress right there would change, because effective stress is equals to the total stress minus the pore pressure, right? So if there's a rise in the water table, the effective stress will go up or go down. If there's a rise on the water table, will the effective stress go up and go down? It will go down, right? So if the effective stress go down, that's, sorry, so if there's a rise of groundwater table, would the pore water go up or go down? It will go up, right? So if this go up, so what happened to your effective stress? It will go down. And the shear stress is a function of the effective stress. So if this is the shear stress, if this go down, you will end up your soil strength to go down here. So simply, like if there's like a rise in the groundwater table, that could also trigger slope failure. So this becomes like very like a typical geotech problem now. Like no matter like you have a recent cut because of civil engineering, activities, you're concerned about the slope. You need to like do a slope stability analysis to like you design for earthquake scenario, also to like because of the change of groundwater table, like all this kind of lateral or mankind activities cause you to think about slope stability, and we need to like do analysis on that. So that will be what we'll be working on this topic. So the best reference for this like lecture is the Duncan and Dwight book. Oh, I don't have it on my bookshelf here. But anyways, like Duncan and Dwight book, I think it's a classic reference. And Dwight pretty much is the one that who redid the U-Texas program, which is a very relevant computer package to do slope stability analysis. But in this course, I highly recommend you to understand the basics, rather than just dive into like a computer package and do a slope stability analysis over there. Everything you should I highly recommend you understand all the fundamental, because the computer packages change. 10 years from now, like there may be other like a type of like software come out, and and even though like you get into a new software, the computer package they use, the computer software package you're using, in order to run the analysis like properly, you need to understand the fundamental. You're given all these options, like different like analysis method. The method of slides, the Spencer method, the block method, or like different like and also you need to input parameters on that, like undrained or drained string parameters. You use like a total unit rate, or you use like a submerged unit rate. So you use phi or phi prime, C or C prime. All those matter. So that's why I highly recommend on the basic understanding on this topic, and that's what we focus on. So my plan is like you don't need a computer package to finish this course. I may change my mind because I just get an email from FLAC. FLAC is a very well-known computer package we use in geotech, and then they open up free versions for substability analysis. So maybe I think it would be a good chance for all of us to learn a little bit of FLAC analysis together on 2D slope stability analysis. Well, I think about it. Maybe I don't think it will happen, but like if I try it and I find out is doable as a first year master students to work on it, then maybe I will give out maybe extra credit for everyone to try like a FLAC analysis. It will be free. It will be free for you to download, and I feel like knowing FLAC will be much helpful than like other commons like our computer slope stability package like UTexas or WSlope or GeoStudio. Those computer package will be like keep update or like keep renew like every decade. So 5 years from now, like whatever like the package you learn will not be as useful as a common source of platform like FLAC we are here talking about. So let's see how things go. But we will focus on the fundamental first, which means we require you to understand the fundamental concept and also do simple calculations by hand. So your final exams, you will expect there will be 1 questions on this topic, and I'll ask you to do hand calculations based on simple slope analysis. Okay, so let's get started. So what is slope stability, or what is the fundamental concept behind? Is first to start to learn this, we start from basic concept, which is the deterministic approach. So nowadays, if you do like a fancy geotech analysis, like we are moving to the performance base rather than like the traditional like a deterministic base, like a factor of safety type of analysis. But yet, like before we get to like probabilistic analysis, we need to like start from basic. So let's talk about the traditional deterministic approach of analysis of this type of problems. So which means like a deterministic analysis, which means you define one case scenario at a time. So when a slope fell, you define one critical slip surface. So it's a circular slip surface, which means you have a center point with the known radius. Yes, is there questions? So you know the radius, and this is your slip surface. We define one critical slip surface. And we use like a typical factor of safety type of deterministic approach. So the factor of safety would be equals to the soft strength. So you kind of like the resistance divided by the demand. So the resistance will be like the soft strength divided by the shear stress. So this is just the driving force. And the soil strength we can make use of the Moore Coulomb. But now you can complicate, you know, in the and that you need to think about which kind of like a parameters you should use, drain or undrained. So if we organize this, we can actually back calculate the drying force. The drying force that trigger failure to be the Moore Coulomb divided by the factor of safety. So remember what is a Moore Coulomb? You have the normal stress and you have the shear stress. So we can define this Moore Coulomb failure envelope in the lab. This is Moore Coulomb. The Moore Coulomb envelope. So the key concept here is we use the factor of safety. And the factor of safety is defined with the shear strength of the soil. And the factor of safety depends on what type of drinking conditions you talk about, drain or undrained. And this factor of safety depends on the slip surface, the critical slip surface. So we assume this. So the first thing we do is like we need to identify this critical slip surface. And there's some engineering procedures to handle this. We'll talk about this later. And if you use any computer package, what they do is actually they will do trial and error. They will try maybe like thousands different like circles going through a site, and then identify the lowest the circles that give you the lowest like effective safety, and that becomes a critical like slip surface. But if you do it by hand, there's some like recommended procedures to do it. But before going into using any computer package, I highly recommend you understand the fundamental. What type of parameter you should use, and when you want the program, you have a bunch of different options to choose, which give you different methodology on calculating the factor of safety, or like how to create geometry and the failure mechanisms. You think about all this. So start from the basics, and then like the next step we will do any like a computer aid analysis for this topic. And the other fact is we make simplifications. This is a deterministic analysis. So we just pretty much like assume worst case scenario. So we assume the factor of safety is constant along the whole slip surface. And if you do it for practice, the procedure is you need to try a couple like different slip surface, and until like you find the critical one that with the factor of safety to be the minimum. So that's the overview of slope stability analysis. And the next thing we need to talk about is, in fact, there's many different like different procedure, different approach to do it. So the geotech engineers like should go beyond this, just become equilibrium static problems. Understanding like each different like a procedure, have its like assumptions and shortcomings, and to know which one to use. When you do it by hand, like you pick the most suitable one, and if you do it like through a computer package, you need to understand which kind of like approach do you choose. And like when you like write a geotech report, you cannot just say I find the factor of safety to be like 1.5. You need to like tell the whole story. The factor of safety is determined by what method through which computer package. So which means we need to understand like each of the procedure, and there's like a tons. There's just many of them. There's many of them. But like we kind of like can characterize them, or kind of like the category of them. There's two main kinds. First is the free body, single free body like a procedure, and the second like a category is the procedure of slides. So there's two different like main approach over there, and from those two approach, there's like many different methods. So first, like for the single free body like a procedure, is you assume the whole mass. So the whole mass right here. So the single body means this one. The whole mass here about the critical slip surface. They move together. They move together. So you consider equilibrium conditions of the failure. So assume the whole thing move together, and also this type of procedure, the equations are written and solved as a single free body. So kind of like static problems that we have been working on. And there's like a different approach. First, the first approach or this methodology. The first is the it's an infinitive slope procedure we'll talk about next, or the Swedish slip circle method. So the Northern Europe, they have the famous geotech problems, quick clay, which is a very weak soil, across the country. So that's why, like in the early days, they are the one that at the leading edge on studying the strength of the soils, and also studying like the slope stability concern. So if you go to YouTube, you can Google like a quick clay. Maybe next lecture I can pay a quick YouTube clip together and watch like some concept failure case history. So when you fail, it's quite dramatic. The whole site like just fall down. And the Swedish people, there's at the early days they have a lot of engineering procedure, and they like at the leading edge on this matter. So they develop a method using the single free body procedure. They call it the Swedish slip circle method. We will talk about this too. The next like a general procedure like people use is called like the procedure of slides. So the nice thing about like assuming the whole circles, so the single free body diagram pretty much like a procedure. You assume the whole thing move together, and the procedure of slides is they cut this into different slides for equilibrium analysis. So they have a vertical slides, and all the equilibrium analysis or equations written for each slide. So the advantage of single free body like a procedure is simple, simple static, quick answer. In the early days, like when there's like we talk about like maybe before the computer time, in the early 19s, like 10s or 1920s, before like even a World War I, like that kind of time, everything is done on paper. So the single free body procedure, you can't make sense. But like when computers started kick in, like even the window time before the conventionals like OS systems, like before that, like there's a bunch of like punch cards and like a DOS system. If you are aware of that in the 40s or 50s, even 60s, the computation power got to be pick up. Then this type of like iterative procedure that like, you know, you find out the equilibrium from one slide and then move on to the next slide, and then like you know, from slide to slide, that like pass on the static the static equilibrium calculations that being feasible, then this method of slides become more and more popular. So you see like the advantage of this kind of analysis is you can discrete your into different elements or different sectors, so such that you can capture the solid properties better. And mathematical wise, like, you know, it's also more precise when you solve for equilibrium on just like a small block of solid body instead of like a huge solid mass. So that's procedure of slides come into place, and somewhere popular method that you still see used nowadays when you have a computer package, the OMS, the ordinary method of slides, the simplified Bishop method, and the Spencer method. Those, like, you know, come into place, and I guess, you know, the expectations for this class, or at least like you know, what I want you to learn, or the learning objective is like for us to know each of the method, what kind of assumptions they are making. For example, some method, they assume the interaction force between slides are horizontal. Some of them is assume you come with a slope that parallel with the critical slip surface. So you know, in between method to method, those like a small change. And like for us, I think, like, you know, to be a better geotech engineers is understand all those like difference. So when you like you know, do the analysis through a computer package, you have the confidence to pick or to choose which methods you use, and you're ready to defend yourself. Because when people challenge you, like, you know, could be from a peer, you know, some worst case scenario, you may even need to go to the court. You need to defend yourself, and people will point to you. Why do you choose this method? Why do you use like ordinary method of slides, not the Spencer? At that point of time, you need to defend yourself. You know, why one is prefer the other ones. So make sure you be aware of that. Like, you know, sometimes some small change favor one scenario than the other, and that's something like, you know, we better know at the back of our mind. So we will go through like this lecture. We will talk. I'll pick a few popular method, and discuss about it. And like, you know, also like we discuss what kind of scenario we should use, like what kind of method, and like, you know, computation wise, like, you know, which method have the advantage, and like all the kind of discussions we'll go through in this lecture. So again, like, you know, this summarizes what I'm talking about. So different procedure make different assumptions to statistize like a static equilibrium. So at the end of the day, it's static problems, but with a very complex geometry, and like can be also like a complex like a scenario that you should think about what kind of parameters for you to represent the solid strength. So you string, or so you use undrained, and like to statistize the equilibrium. You know, what is the reaction force from each slide? You need to think about it. So those we go into details. And one more time, it's like, you know, don't be so naive that like you have a computer package. You know, your computer could be GeoStudio, could be like a UTexas, could be FLAC models, like. But like, if you don't understand the fundamentals of each method and the fundamentals of how to tackle all this problem, you know, to me is you just like a computer. Anyone, you know, gets able to run the program, or nowadays with even AI can do a much better job than like you know, for someone just like clicking the program. But like as a geotech is to understand all the small difference between each method, and also like which design parameters you should be used. So And like a difference depends on the method and also the analysis procedure. Sometimes the static equilibrium may not be stabilized, and also for us, geotech, we need to understand which method is stabilizing the equilibrium and which one is not. And for the one that is not stabilized, the static equilibrium, why not? And what is the trade-off? Because remember, all this happens like many years ago, and back to the old days, stabilizing equilibrium for all the slides there with like complicated geometry that like is not perfectly horizontal or vertical. Doing all the calculations on paper could be like impossible. So that's why oftentimes engineers, they make assumptions to speed up or to simplify the calculations. Sometimes they trade off the requirements of being like to fulfill the static equilibrium. So our job is to understand like all the shortcomings. So any questions? Okay, very good. So let's get started. So first, let's talk about infinite slope. So infinite slope is the one that we assume when failure happens. So this is the only one. This is the only one that handle when you have like kind of like a layered type of like a failure. So it's assumed is extend infinitively in all directions. That sliding is occur is along a plane that parallel to the face of the slope. So it only happens for cohesionless soil. Oops. So when you have sand and you have gravel, so when you fail, it could be all the leveling or like the shallow surface failure that occur. So a layer of like a material got slide off. So it only happens pretty much. It only happen for cohesionless gravel or sand slope. When you have a clay slope, very likely you have the circular critical circle type of like failure. So for this like infinite slope problems, we can use this approach. So that's why like when you become practice engineers, when you have a clay, when you have clay site, then it won't happen. So this is like a waffle. I got questions there. So this is. Okay. It could also happen when you have the sliding. Parallel to slope surface. The slope face. For example, a block of soil over a walk. So when you have very like a smooth contact, the whole like plane slide off. This can be used too, and very likely it's just cohesionless soil. So all this slope stability analysis is also like depends on the understanding on how to set up this type of problems or the geometry. So we first of all we assume this is the failure surface. and thus come with an orientations angle of alpha. We assume the whole diagram here, we have a unit thickness. So the dimensions go out to the page is a 1 unit. So we assume now we just look at one individual block to simplify our problem. We just look at one individual block. We assume this block have a weight of W. And we know the dimensions of this block. Assume a dimension B right there. And we know about the thickness of the block, or the height of the block. We know the unit weight of the soil. We assume the reaction force on this block is N, and the strength come from the resistant force to resist the block to slide is the tension force or the friction force between the sliding to be occur. And we also assume we need to know the reaction force. You want to need to. And we take advantage of the whole slope being infinite. So it only works for infinite slope. The reaction force is equal to each other, E1C to C2. So if we draw our force diagram, so everything will feel like equilibrium. And if we draw the the force diagram, this is the rate, and the reaction force come with an angle of the slope orientation. And if everything is in equilibrium, we should have a closed loop. And if we do our math to do the shear force, which is equals to the friction force right there. So what being driving the slope to slide is the rate, is the self rate of the slope. The rate, times sine alpha. And we can calculate the rate because we know the unit weight of the soil. So unit weight times the area or times the volume. Now we have a unit like a thickness into out of the page. So this is the unit thickness. We also know the normal force. So when failure occurs, we got the friction force equals to the normal force times tangent phi pi. So if we plug in those equations right here, so the W sine alpha will be equals to W cosine alpha times tangent phi pi. If we simplify it, the tangent phi pi will be equals to W sine alpha divided by W cosine alpha. Which means the tangent alpha equals to the tangent phi. So which means if our orientations, oh, is it better now? So someone tell me they cannot see my screen. So my alpha will be equals to, or when alpha greater than the friction angle, then failure will occur. So the concept of the methodology of infinite slope is telling us by the symbol symbol like body diagram, and for the simple assumptions that we are at an infinite slope, we don't take account into the or the like the lateral force, they cancel each other. Under those like a scenario, all those assumptions, we would conclude that if the slope is greater than the friction angle, then failure could occur. So that's the simple analysis of infinite slope. Okay, questions? You guys good? And the other approach right there, very similar. I don't want to write the whole thing again, but like when they calculate that instead of a free body diagram, they calculate in terms of stresses. So they think about the stresses on the block slide that we mentioned. So is the stress on it is the tensions or the friction force divided by the area, and then they compare with the normal force right there, and then they use the shear strength of soils equations. But this is the Moore Coulomb, the like C equals 0 for sand or gravel. So they use the Moore Coulomb right there, and then like they assume the potential failure plane, considering the factor of safety is the soil strength divided by the shear stress. So they call the shear stress right here. So with this like stress analysis, back calculating, assuming the factor of safety is 1.0, and back calculate the failure conditions, and then they get back the same thing. When the orientations, when the slope is greater than the friction angle, then under the conditions of infinite slope, failure will occur. But like our job is to understand like all those analysis or all those like scenarios, like what happening there. First, we assume you have like a plane type of failure. You have a plane failure plane, And also we are only working on cohesionless soil. So if you have a site that happens to fulfill those conditions, then you can uh, conduct your slope stability analysis based on the infinite slope approach. And at the end of the day is comparing your sloping angle with the friction angle. So so there's for this method, there's phi equal phi prime. Well, it depends. It depends on whether you're in total stress analysis or total stress or effective stress analysis. So it does only work. This method got simplified when there's like no water in the slope. When you have like a water in the slope, then you also need to bring in the water pressure. Actually, it's a little bit more complicated. So Tommy, I think is you're right. For this method, it's for total stress analysis only when there's no water. When it says water, you will get more complicated. So when you have water, there will be like extra force right there. So you have your reaction force, and also you need to think of the water pressure adding on the slope. So they'll be more complicated. Any questions? Remember, when we talk about this, we have like a different category. So we are kind of like at the simple one where we just treating the whole sliding mechanisms as a single free body, a single free body. So it works, as long as we are not breaking up the slide. Sometimes it works because the whole thing moved together. But if you have a site, if you have a slope like this, so this is a failure plane, and if you have slope that have different material look like this, so this could be like a sand, this could be gravel, this could be sand, and if you want to use the method of the single body method, that would be like it would be much more challenging, or much more questionable whether you can use this method, because if you're cheating, if you're cheating at the whole failure block as a single body, but you have different material right there, then it become a concern. So those a simple procedure is nice, the method is simple, and the concept is simple, but as a geotech, we need to understand all the limitations and all the assumptions behind. Okay, next is still the same. Is the single body method, but now this method is the Swedish circle, and we assume we have we have a slip surface, but now we assume we have slip surface. So when we fail, we assume there's a critical slip surface. So the slip surface is assumed to have a circular arc, which means then we can identify the center and also the radius. So this is the center. And also the radius. So we assume we know this circular arc, and then like we can calculate the moment about the center of circles, and then knowing the moment we can find out the factor of safety, and the friction angles is assumed to be 0. So for this like a Swedish circle method, it only works for clay. So it only works for cohesive material. Alternatively, this method called E equals 0 method, because we only consider the cohesions only. So we have the slip surface right there. And we assume we know the geometry, so we know the length arrow right there. And since we defined the circular arc, so we can identify the center of mass. So this is the center of mass of the circles, and the center of mass of the circles identify like the rate of the whole slide of the whole circles, and we will know the distance between the center of mass and the center. So now we become a single body. Again, the whole thing is a single body, and it becomes a static problem. And we solve this static problems by taking the moment to the center. So we consider 2 moments now. So the moments of the driving mass will be, so the driving force for this style of problems will be equals to the force times the moment arm. The force is the weight, and then the moment arm will be the distance from the weight to the center, because we are taking moment to the center. And the moment for the resistant force will be equals to the shear stress. So when the whole thing slides, the resistance comes from the strength of the soil, the shear strength of the soil. There's a shear strength of the soil kind of holding the body mass. So the resistant force will be equals to shear strength of soils times the length of it, and then times the radius of the circle. And the ratio between the two give us the factor of safety. So the resistance divided by the driving, so the resistant moment divided by the driving moment give us the factor of safety. So very simple concept here. Any questions on this part? On the simple Swedish circle method. So things can be very complicated. The first lecture, when we get started, we just start at the most simple concept of methodology. Some of you may have seen this already. If it happens, your undergrad educations, at 4,000 at the senior level has a slope stability constant. You may have seen this before. But if you happens you only take the foundation design, but you don't have any slope stability analysis experience, this could be something new. So I start from the most simple method, which is the single body method. And for the clay, the clay will be like for the Swedish circle. So there's a questions like how many times we recommend to run this this test to develop factor safety? Very good questions. Very good questions. So if with well we should look at this with or without a computer. With a computer, the computer package, they use trial and error, however times it needs, maybe like a 10,000, I don't know. So the computer code is pretty much still keep trial and error until like they have a tolerance smaller than your smaller than the threshold that you set. So they keep trying, so the computer, what they will is like they try and error on. They try if they have grids, you set the boundaries of the grids that being reasonable, within the site. So they try all those points. So they will have almost like an infinite circles until like they find the smallest factor of safety. That is with a computer. Without a computer, there's some like a recommended procedure for you to try to send this. So I would say maybe five to 6 times to be very reasonable. So you have some guidelines to try the first trial, and then you would try like maybe another point here, and then see get a sense on how sensitive is the factor of safety changing, and then to a point that you feel comfortable that is your smaller factor of safety. And that was the old day, and to be frank, nowadays pretty much everyone uses the computer package. But my requirement and my recommendations is for all of us to understand the basic. When you have the choice to choose which method to use, you need to be ready to defend yourself. Why that method? So, any more?
We're talking about the slope. So the fundamental is this. Well, the deal here is I wish everyone understand the fundamental. So we can when you operate, when you use the software package in the future, everything makes sense to you. Because another point is you never know what kind of computer package you have when you go to work, and those packages are not cheap. We may be teaching you Texas, but go to work, you may have a GeoStudio. We may be teaching you a Slope W, but when you go to work, it will be another kind. And who knows 5 years from now what kind of a new package you have. So it's more important to understand the fundamental. So whatever computer package comes to you, you understand, or you even can develop your own computer package. I have some friends they can develop apps in the cell phone now, try to make money from it, slope stability apps for field engineer to do quick calculations on site. And at the end of the day, those are the static equations. If you are using the single free body procedure, it shouldn't be too bad. And at graduate level, as a graduate students, I think you should able to handle using MATLAB or using a Python or even Excel to code it, create a easy use computer script, program script to program the single free body a procedure slope stability analysis. But using the a procedure of slides, you will be a little bit more complicated. Highly depends on how whether you fulfilling the static equilibrium. Whether you can fulfill static equilibrium. So we're going into details on that. So at least I think we can finish this slide. So this Swedish circle method, it has another capability. Another capability is a little bit more flexibility, or make this method a little bit more powerful. Yes, in fact, you can discrete this is your critical surface again, a critical slip surface again. You can discrete the length right there based on the geometry. So for example, if you have like a different soil layers like this, right? So you have different soil layers. I don't know how to draw it, but I try my best. So maybe if you have different soil layers, then it turns out you have different like soil cohesions, soil properties. Then you can have a little bit flexibility to do this analysis. Because at the end of the day, right, if you plug in these equations, the factor of safety will be equals to the resistance, which is the shear stress times the length times the radius divided by the driving moment, which is the rate times the moment arm. So if we try to like break this into different layers, the moment of resistance, or actually is the factor of safety, could be equals to these summations. So the radius is the same, right? The radius is constant for each of the terms here. So this is the radius. The radius is constant because we are still talking about the same circle, the same slip surface. So the radius is the same, but the summations of the properties will be different. So we can do it this way for this Swedish circle. So this method like is a single body procedure again, but the nice thing here is it gives us the capability to break down into different segments. So that's one example over there. And back to the old days before computer program, you know, when the old folks, like I mentioned about computer programs, so this spreadsheet is the computer program. So you have different, well, they call slides over there, but don't be confused. No, so David's asked the questions like each. Oh yeah, you're right. So it has a different moment arms. It has a different moment arms. So this will be different weights and different moment arms. So you will be, well, this will be take care of the moment arm will be back within the in the equations right here. So back to the old days, this will be the software, computer software people use. So when you have different like a length of each segments, and then on each segments you have different like orientations, and also like you define the thickness. So we'll come up with this like a kind of like a procedure. So you can define the rate, and then you can define the length of it.